Okay, so this was covered in the last class. We have done some hands-on examples on go back in and then selected repeat. And you can see there are 3 rules we have used for go back in, and the similar 3 rules with a different approach we have used in selective repeat. So the basic difference is go back in is very inefficient in terms of discarding the out of order packets. So those packets must be retransmitted even if received by the receiver correctly. And then in selective repeat, only the lost packet will be retransmitted, because selective repeat will store or buffer all out of order packets and only retransmit the lost packet. So that was the basic rules about go back in and selective repeat. And we were given one particular question of solving go back and selective repeat for n equals to 5, and then packet 3 and packet 5 was missing, and we have to show up to the successful transmission of 7th packet. So let me give the solution first before going to our today's topic, that is TCP. We'll cover TCP today, and before going to the lecture, just let me inform you that some of the features of go back and selective repeat both are used by transmission transport layer protocols like TCP as advantage. For example, go back N has definitely some disadvantages in terms of utilization, efficiency. It is less efficient because loss of bandwidth because of discarding those packets. But at the same time, go back N will require less amount of memory, right? Because it will not store out of order packets, so it will require less memory. And if a protocol will store out of order packets also, it cannot hand over the packets to the upper layer unless the gap is filled up. So that's why those protocols like selective repeat will require more memory. So in that sense, go back N has one advantage also, using less memory, and selective repeat needs more memory, but memory is more available now. So the updated TCP protocols actually uses the properties of selective repeat and also some property of go back N as advantage. We'll see when we start TCP. Okay, before going to TCP, let me give the solution. Okay, so stop presenting here and start presenting here. So let us go for the solution. As I said, our requirement was doing solving for both go back in and selective repeat, where n equals to 5, packet 3 and packet 5 or packet 6, packet 3 and packet 6. Okay, packet 6, packet 3 and packet 6, that is serial number 6 packet lost, and then we have to show up to 7th packet. So successfully transmitting up to 7th packet. So let me solve side by side. So this is A, this is B, and this is go backend. Go backend. This is go backend, and value of window is 1, 2, 3, 4, 5 until changed. So packet 1 will be transmitted, packet 2, packet 3, packet 4, and then packet 5. Packet 1 is correctly sent, packet 2 correctly sent, packet 3 lost for some reason. Whenever packet 3 is lost, let me draw a timeout for packet 3. Okay. If anybody has any question, please, you can ask. Okay, no problem. Then packet 4 correctly gone, packet 5 correctly gone. Now sender has to wait because value of n is 5. So sender is finished, and this is timeout of packet 3, right? Okay. Now come back to the receiver side. Okay, so come back to the receiver side. Now receiver receive packet 1, acknowledgement 1, receive packet 2, acknowledgement 2, then packet 3 is lost. So packet 4 received, what it will do? It will discard packet and it will send the last in order acknowledgement. Packet 5 is received, it will discard the packet and send the last acknowledgement. So this is how the receiver will react. Now let me, you can put anywhere this, yeah, maybe this one after the timeout, no problem. It's not a problem. So now receiver part is complete. Receiver is now waiting for the new packet. So you come back to the sender part. For the sender part, whenever acknowledgement 1 received, a new packet can be sent, right? Because this is okay. Whenever an acknowledgement 1 is received, the window will move now 2, 3, 4, 5, 6. So that's why a new packet can be sent. That is packet 6, right? And we know packet 6 will be lost. So again, for some reason, packet 6 will be lost. Whenever packet 6 will be lost, let us give a timeout for packet 6. So there is no relationship of packet loss and timeout. So timeout is whenever a packet is sent, timeout is sent. But we will only show timeout for the packets those are lost. The other packets will assume no need to show the timeout because the acknowledgement will come back within the timeout. So after receiving the acknowledgement 2, what will happen? Window will again move 3, 4, 5, 6, 7. So packet 7 will be retransmitted, will not retransmitted, packet 7 will be transmitted by the sender. After receiving the duplicate acknowledgement, what will happen, anybody? After receiving the acknowledgement A2 for P4, what will happen? Anyone?
Sorry, it will resend A2.
Sorry, Rohim?
It will resend acknowledgement 2.
Resend what?
Acknowledgement 2, sir.
The acknowledgement is already sent by the receiver. I am asking what the sender will do now. After receiving the acknowledgement 2, that is duplicate acknowledgement. See this point. What now sender will do? Will it send a new packet? Yes or no?
So packet 3.
Yes, sir. Packet 3, sir.
Packet, then packet 8. Then it should send packet 8.
No, no, no.
Why packet 3? Packet 3 timeout is not yet done. I am not yet in the timeout. I am just in the point. Okay, one more point. One more point. You have to consider every single point. When the acknowledgement is received by the sender, sender will do something. When timeout occurs, sender will do something. There is no, when you draw, maybe you draw this point, receiving acknowledgement point and the timeout at the same case, but in case of execution, that will be sequential. Which one comes first? So in this case, acknowledgement comes first, so you have to first decide whether or not to send a new packet. That is the question. Will a new packet be sent? Should it? What will be sent here?
Yes,
A
sir.
new packet sent, or it will ignore?
No,
After
sir.
receiving acknowledgement 2, it will send a new packet or it will ignore the acknowledgement? Sender.
Sir, ignore, sir.
Ignore, right? Ignore that, because the window cannot move. Why? Because this is a duplicate acknowledgement. See, this is duplicate, right? This is duplicate acknowledgement. This is duplicate acknowledgement, because it is already sent once. So it will not
Yes, sir.
retransmit. Now, after this point, the timeout occurred. Now you have to first act based on timeout. So what will happen? You have to now retransmit. Now for during retransmit, you have to retransmit packet 3 and then up to all the packets. So packet 3, packet 4, packet 5, packet 6, and packet 7. Okay, see, 5 in value of n is 5 now, so you have to send 5 packets again. Now packet 3, packet 4, packet 5, packet 6, and packet 7. Now sending, and for the duplicate acknowledgement to this point, again there will be nothing. Window cannot move, because window will only move when the sender receives acknowledgement 3, right? Otherwise window cannot move. So it is very simple. If window does not move, you cannot send a new packet for any duplicate acknowledgement. So in this case also, it will send nothing. Now at the receiving end, receiver will receive, when it receives packet 7, the earlier one, again what it will do? Discard, and then it will send duplicate acknowledgement, again retransmit. When packet 3 is received, then what? Acknowledgement 3. Packet 4, acknowledgement 4. Packet 5, acknowledgement 5. Packet 6, acknowledgement 6, and then packet 7, acknowledgement 7. So these are all in order, right? Now this is actually this is actually end of our solution, because packet 7 is correctly received by the receiver. But one thing you have to keep in mind, packet 6 was earlier, packet 6 was lost, right? Now you have to take care of this. If you finish here, your answer is incomplete, because packet 6 was lost. Even if packet 7 was correctly received by the receiver, you have to take care of this timeout, because timeout will be another event, right? Now tell me, what will happen? Okay, before that, you can just put all the acknowledgements here. Okay, you can just complete this, and you can put all the acknowledgements somewhere here. Now what will happen in this point after the timeout? Anybody? This is a crucial point. Although if you think about receiver side, receiver has received all the signals, but you have to take care of sender, because
packet
sender.
6 and 7 will be retransmitted and
Very
it will be
good.
discarded.
Very good, Shahada. Packet 6 and packet 7, because sender window will not update until acknowledgement 3. It is still showing 3, 4, 5, 6, 7. So it is not sure whether receiver has received 6, 7, right? So what it will do, according to rule 3, it will retransmit packet 6 and packet 7. That means lost packet, and all subsequent packets. Now, after packet 6, it has only sent packet 7. Okay. So it will retransmit these two after the timeout. Now, in the receiving side, you can say, okay, packet 6 is received, but what will be the acknowledgement now? This is another question. Because packet 6 is redundant, receiver will understand this is redundant. I have already received packet 6, but again, sender sent me packet 6, but it needs to send an acknowledgement. What will be the acknowledgement number? Acknowledgement 6 or acknowledgement 7? Shahadat, do you have any idea? According to the rule said last in order acknowledgement. What is last in order acknowledgement? Acknowledgement 7.
7.
Okay. So this is, you have to just follow the rule. If it sends acknowledgement 6 because it received packet 6, then it is against the rule, because the rule said last in order acknowledgement. So last in order acknowledgement was A7 from the receiver side. So you cannot make it A6. Clear? So that is the actually
Yes,
end. Although receiver has received packet 6, packet 7 twice, we have nothing to do, because this is the rule for go backend. In this case, if it is n equals to 3, we might have a different answer. N equals to 4, we might have a different answer. For n equals to 5, you have to complete like this. Any question, anybody? Okay, then let us okay, now just one more thing. When A3 is received, acknowledgement 3 is received, here, only here, the window will move 4, 5, 6, 7, 8. It can send a new packet, but you don't need to show that. Just I wanted to make sure when window will move. And if window does not move, sender cannot send a new packet. So only when acknowledgement 3 is received, sender can send a new packet, because window will move. Okay, that is end of solution of go backend. Now let us do the solution for selective repeat. So this is selective repeat. Now let us do the same thing. N equals to 5. So initially the window will be 1, 2, 3, 4, 5, same. So packet 1, packet 2, packet 3, packet 4, and then packet 5. So packet 1 is sent, packet 2 is sent, packet 3 somehow lost. Whenever a packet is lost, let us set a timeout. Packet 4, and then packet 5, and then sender needs to wait. So same thing. Now, if you go back to the receiving end, packet 1 is received, so acknowledgement 1 is sent. Packet 2 is received, acknowledgement 2 is sent. Now packet 4 is received. This is out of order, right? So what receiver will do?
buffer it.
Sir, discard.
Buffer. Okay. It will not discard, because this is selective repeat. So rule
Yes,
is
this is
different
this will be
here.
buffer, sir.
It will buffer. Okay.
Buffer.
And then it will transmit what? Acknowledgement
Acknowledgement 2, sir.
Sir, 8.
4. Every rule is different for selective repeat. You can see your class note. Okay. So it will be individual acknowledgement. It will buffer out of order, and it will send individual. So it's packet 4, so it will send acknowledgement 4. Then packet 5, again it is out of order, so buffer, and then send acknowledgement 5. So that's right.
Yes, sir.
Okay. So now you just send the acknowledgements here, maybe third one here, maybe fourth one after the timeout. But again, where you should place the acknowledgement is up to you, no problem. You can put all the acknowledgements after the timeout. You can put shorter timeout. You can put longer timeout. Doesn't matter. Every answer is correct as long as you don't violate the rules. Okay, now receiver part is complete. You come back to the sender part. Whenever acknowledgement 1 is received, we know window is moved 2, 3, 4, 5, 6. Whenever acknowledgement 2 is received, we know window is moved 3, 4, 5, 6, 7. So after receiving the first acknowledgement, packet 6 will be sent. After receiving the in order second acknowledgement, packet 7 will be sent. So packet 6 is lost. Again, if packet 6 is lost, let us set a timeout for packet 6. So this was actually timeout for packet 3. And then this is the timeout for packet 6. Okay. Now, packet 7 is retransmitted. It's not retransmitted. Packet 7 is transmitted. Okay. What will happen when acknowledgement 4 is received? Anybody? Taki, can you tell me at this point what will sender do when it receives acknowledgement 4?
স্যার এটা স্যার P8 সেন্ড করবে না স্যার কিছু সেন্ড করবে
P8. P8 send or nothing?
নাথিং স্যার নাথিং ইগনোর
Good, very good. Nothing will send. Why nothing will send? But just you have to think about the window. The window is up to 7. Will the window change? Until acknowledgement 3 is received, window can never change. Although packet 4 and packet 5 is now stored, but there is a gap with packet 3. So acknowledgement 3 will not be received. Until acknowledgement 3 received, window cannot move beyond 3. Is it clear? So that's why it will do nothing. Now after the timeout, what will happen? Kaushik, can you tell me? After the timeout, what will happen?
No,
What will
sir.
happen? You cannot
I
tell
don't
me.
know, sir.
Okay, Nibir, Nibirujjaman, Nibir, can you tell me? Nibir, are you there? Ashrafun?
Chat লিখছে স্যার নিবিড়।
Okay.
Sir, he just texted me.
Ashrafun, can you tell
Yes, sir.
me what will happen after the timeout? Just this point here, this timeout. After timeout, what will happen? What will be retransmitted? Which
P6.
packet will be written? No, it's a timeout for P3, right? It's a timeout
Oh,
for
in
P3,
here.
not P7. Yes. Yes, in this point, the first timeout for P3.
In this point,
packet?
then packet 3 would be
Retransmitted. Any other
taken.
packet
Yes.
or only packet 3?
Sir,
At first packet 3.
No, what
Then
the rule
packet
says
4.
for selective repeat. Is it only packet 3 or all other packets also? You have to
Only
make it
packet
clear.
3.
Right, only packet. The rule says in selective repeat, this is why it is selective, because it will only retransmit the lost packet, not the all subsequent packets, unlike go backend. So only packet 3 will be retransmitted. Okay, so packet 3 will be retransmitted here. Now after receiving A5, which packet will be transmitted? Anyone? Dihan Pathan,
Yes,
can you
sir.
tell me after receiving this point? Okay, observe here. after receiving acknowledgement 5, what sender will, which packet will be transmitted by the sender, or no packet will be transmitted? A5 is individual acknowledgement received by the sender. What the sender will do? Anyone else?
I do not know.
Anyone else? Abu Sajjad, can you tell me?
I don't know, sir.
You don't know. See, we have, this is the third lecture we are giving on this. So that is the problem. I think many of you didn't try yourself. Maybe you have gone through the solution of others, solution by me to understand, but you did not try yourself. That is the problem. If you try yourself and you have a solution with lots of errors, no problem, then you go for the solution. This is one time, and then it will be everything will be clear, should be clear. Okay, anyway, Shahadat, is there any new packet retransmitted?
No, sir.
No. See, very simple. If it is clear to you, this type of examples, very, very simple. This is logic. You are a computer science student, you are an engineering student. So this logic should not be a matter to you. Just matter is whether or not you connect the concept with your idea. As long as there is no change in the window, then no new packet will be retransmitted. Simple. No new packet will be transmitted. Okay. So it will be nothing. Now come back to the receiver send. Okay. What receiver will do? Receiver will receive packet 7 again. This is out of order, right? So buffer, and then it will send acknowledgement 7. Now when packet 3 is transmitted, this is in order. So it will send acknowledgement 3, right? See, selectivity is much more clear and easy to draw. And then let me show this here and this one here. Before that, there is a timeout. Okay, so receiver has received packet 3 and send acknowledgement 3. Now come back to the sender side. Sender will send nothing here. Again, window is not moved. In fact, window will not move until acknowledgement 3 is received. So after the timeout, what will happen? Only packet 6 will be retransmitted. So packet 6 retransmitted. And after receiving packet 6, receiver will send acknowledgement 6. Now see, from the receiver's point of view, if you draw the buffer, initially there was 1, then 2, then there was 3, there is a gap, then 4 received, then 5 received, then there was again a gap, and then 7 received. Okay, so after retransmitting packet 3, this gap is filled up. After retransmitting packet 6, this gap is filled up. So this is how selective repeat works. Now you can show the acknowledgement like this. Okay, so this is the end because receiver has received all 7 packets. There was a gap with package 3, acknowledgement 3, there was 6. Now one more thing, when it receives acknowledgement 3, what will be the condition of window? 6, 7, 8, 9, 10, right? 10, right? Okay. After receiving acknowledgement 7, what will be the, after this point? 8, 9, 10, 11, 12. Is it clear?
Yes, sir.
anybody has any question. So this is the solution. See, selectivity much easier to understand. Okay, is it clear, everybody? So that is actually end of section 3.4. I have given you much more number of examples, many examples, and time to understand. So I hope this will be enough for you to understand. Just we have followed those 3 examples and we have solved this. Okay, now let us conclude 3.4 and now go back to 3.5 and let us go back to our lecture on chapter 3. Okay, so let me open okay, let us now start TCP, that is section 3.5. So we have covered section 3.4 with go back and select to repeat. And as I said, there are some properties of go back and select to repeat. Those type of algorithms can be implemented in data link layer also. But now in section 3.5, when we start to read transmission control protocol TCP, now definitely we are concentrating on transport layer. Okay, so this is about transport layer. Okay, already we know some of the properties of TCP, that is it's a point to point, that means one sender, one receiver. So both sender and receiver are end systems. We know there is no intermediate node that works with transport layer. And also it's a reliable protocol. Reliable means if some packets are lost, then those packets will be retransmitted by TCP. And another thing is it's an in-order byte stream. In-order means if the segments come out of order, those will be in-ordered by TCP. And there is no message boundaries. That means TCP will take data from application layer. It can be an email, it can be a file, it can be audio file, video file, doesn't matter. TCP will treat that message as a number of bytes, for example 100 bytes or 1000 bytes or 20,000 bytes, and then convert into segments and then transfer those segments to the receiving end, and receiving end will reassemble all those segments into the original message, email or file and hand over to the application in the receiving layer. So that is called no message boundaries. TCP does not need to understand where the email starts, where the email sends, is there any a single email or multiple email, is there a single file or multiple file, doesn't matter. It will just work as a number of bytes. So that's why it is called byte stream. Okay. Okay. So another one is a full duplex. That means the communication is bidirectional, and each segment has a maximum size. It is called maximum segment size. One important property or keyword used by TCP is cumulative acknowledgements. Cumulative acknowledgements means acknowledgement can never decrease. I think we have already saw this in go back N. So if one or more segments are lost, go back N will return the receiver receiving out of order segments will return what? Will return the last in order acknowledgement. That means this is called cumulative acknowledgement. That means acknowledgement can never decrease. Just in our last solution, can you remember when packet 6 was retransmitted, receiver received packet 6, receiver sent acknowledgement 7. Can you remember just a few minutes back? I showed, right? So in that case, A7, why not A6? Because A7 was last in order acknowledgement. So if I send A6, that means I am decreasing the acknowledgement. When I send cumulative acknowledgement, you will never see decreased acknowledgement. So that is why go back and uses cumulative acknowledgement, and also TCP will use cumulative acknowledgement. Okay. So in case of any data loss, it will never send the next acknowledgement. It will only send the updated last acknowledgement. Anyway, TCP is also a pipeline protocol like go back and like selective repeat. TCP is a connection oriented protocol. We will see how the initial connection must be established before the data will be sent. And one more thing is TCP is flow control. Flow control means we have already discussed in the layering concept. We will see a more elaborated picture in this chapter also. This means sender will not overwhelm the receiver. So sender will send the number of bytes available at the receiver's buffer. So in that way, there will be no overlapping or overflowing of the receiver's buffer. That is called flow control. And one more thing is congestion control. We will also learn congestion control here. Congestion control is not only receiver's buffer, it's about the capacity of any link. If data is coming more in a more higher rate than the capacity, then what will happen? The intermediate device like router will store the packets in buffer. Buffer will increase, queue will increase. At one point, if buffer is full, still it is over the capacity, newer packets are coming, then those packets will be lost. Already we have discussed this about packet loss in chapter 1. There are two types of packet loss. One is for error, another one is for buffer full. Can you remember in chapter 1? So congestion control deals with that. If the arrival rate is more than the capacity, then jam will happen, congestion will happen. So we have to solve this, and TCP also controls that congestion. So this is the overview. Now let us go a little bit more in depth. To understand the mechanisms in TCP, you have to understand the TCP segment structure first. That means what are the fields in the TCP header, and the TCP segment, we call TCP segment when it divides the application layer data into different segments, and each segment has application data and corresponding header fields. So you can see every row here is 32 bits. Source port, destination port. Already we have seen in UDP header, right? Source port is 16 port, 16 bit. Destination port is 16 bit. 16 bit means 2 bytes. So the first row contains a source port and a destination port, same as UDP, and one single row is 32 bits. That means 4 bytes. Now there is another field called sequence number. Now some of these fields will be used to synchronize. Since TCP is a reliable protocol, these numbers will be used to ensure that sender and receiver knows each other's state. That means when sender sends some data, receiver sends some acknowledgement, then sender will know which data is received by the receiver and which data is not received by the receiver, so that it will able to retransmit. So that is, there are some fields. First one is sequence number. Okay, sequence number means what? Segment sequence number. See, if a sender creates 100 segments from the application layer data, one idea could be like numbering the segment as 1, 2, 3, 4 up to 100, right? But it is not like that. Why? You will be clear a little bit later. The sequence number is not the segment number. The sequence number is what? The sequence number is the starting byte number of the segment. So if a segment starts from byte number, for example, 101, and it contains 50 bytes, right? Maybe this is the second segment, but the sequence number will be 101, not the segment number 2. Okay, so that is the idea. Why? Because we already said TCP is a byte stream. TCP sees the messages as a number of bytes. So every segment will be identified by the byte number of the starting byte of the segment. So that is sequence number. Whenever sender sends a segment, it will create a sequence number that will be the starting byte number of that particular segment, not the segment number itself. We'll see an example just little after. Second one is acknowledgement number. So whenever a receiver receives a segment with some sequence number, for example, it receives a segment with sequence number 101 and then 50 bytes of data. So what receiver will do? Receiver will create an acknowledgement number. That means it will calculate what is the byte number up to which it has been received and what is the byte number of the next segment it is expecting. So acknowledgement number, basically, you can see the definition. It will be the sequence number of next expected byte. Sequence number of next expected byte. And also in that case, it will indicate, okay, this is an acknowledgement of the previous segment of any segment sent before. So in that case, it will turn a bit on. That means there is a bit called acknowledgement bit A. It will be 1. Whenever receiver sends an acknowledgement, it will be 1. There are some other bits in the header. We'll see later. Okay. Then there are application layer data. Definitely application layer data in the body, other than header, data sent by the application. And then there is a checksum. We know checksum is used for error detection. There is a field called options. It's a variable length options field. That's why I told you before that there are 1, 2, you can see how many rows. 1, 2, 3, 4, 5. Except options field. So there are at least 5 fields in the TCP header. If there are options field, then there can be more. So if there are 5 rows, then how many bytes? We know each row contains 4 bytes, right? 32 bits means 4 bytes. So 5 into 4, 20 bytes,
20.
right? So minimum header is 20 bytes. If you use options, then header size will be more. But if we
24
don't use
bytes.
options, any question?
No, sir.
Yes, Shadat, yes. Then if we don't use any options, that means we have to use at least 5 rows, so 20 bytes. That information I have already given you when I told about UDP, right? UDP has how many bytes as header?
8 bytes, sir.
Right, 8 bytes. Now compare to UDP, you can see here at least 20 bytes for each segment, and it can be more if you use optional field, but we don't need about optional. We need to understand these 5 rows only. And there is another field, you can see there are some other like header length. Okay, so since header length can be variable, it can be 20 bytes, it can be more. That's why there is a field which specifies what is the header length. Then there are some part of the header not used, and there are some other bits other than A for acknowledgement. There are some other bits like R for reset, RST, R for RST, reset. It is used when both sides somehow lost the synchronization. So it will go back to some earlier state. In that case, one side will set that reset bit 1. So other side will understand, okay, we have to go back to a particular step. Then there is a SYN bit, SYN for synchronization. We will see when we go through that connection establishment phase. This SYN bit is used at the first whenever a client establishes connection with the server. Okay, and then FIN, again FIN for finish. That means when client wants to close the connection, this FIN bit is used. So these bits are only used for connection management. RST, SYN, FIN, only for connection management. And then there is a receive window field, another important field, receive window. This is used for what? This is used for flow control. That means every time the receiver sends an acknowledgement, it will calculate how many bytes space, free space it has in its own buffer, and then it will advertise this. It will say, okay, I have 200 bytes in my buffer, so don't send me more than 200 bytes. That is the value of receive window. So that is how flow control is implemented, right? So number of bytes receiver willing to accept, or number of bytes free in the receiver's buffer, that will be advertised through this window. And there are some other bits like congestion notification, don't worry about those. And there is another one, urgent data pointer, don't worry about that. So basically you have to understand all other header fields like source port, destination port, sequence number, acknowledgement number, bits A, R, S, F, 4 bits you have to understand clearly. You have to understand receive window, you have to understand checksum, but don't worry about the other fields. And when we go through the reliability mechanism provided by TCP, like go back and select to repeat, you will see that TCP will always use these 3 fields like sequence number, acknowledgement number, and receive window. So these 3 fields actually implements the synchronization mechanism between sender and receiver. Any question, anybody? Any particular field? All the description of different fields you can find in the textbook. Okay, so hopefully you have to go through the textbook, and just let me skip this for now. So as you can see the relationship between sequence number and the bytes in the header, see, and the bytes in the segment. So sequence number is byte stream number of first byte in segment's data. So if sender sends a particular segment, it sends a number of bytes, the first byte will indicate the sequence number. Okay, and also it shows the acknowledgement number. So after receiving a particular segment, receiver will send +1. That means, okay, I have received up to this number of bytes. Now send me from that byte, just +1. Bytes received +1. That will indicate acknowledgement number. So for example, now let us go to examples. I know it's very tough to understand everything from the theory, but if we see some examples, it will be clear. Just try to connect those field descriptions with the example we provide in the class. So this is an example of Telnet. You know, Telnet is an application where it is used for remote login. For example, I can use a management PC or PC to connect to my router of my network. Anyway, the characteristics of this application is it sends one character at a time. It sends one character at a time. So if you press one character, immediately it sends 1 byte. You know, one character is how many bytes? 1 byte, right?
Yes.
In programming also, one character means 1 byte. So any application, if it sends byte by byte, character by character, that means it will send 1 byte for every segment. Now in this example, you can see user type C, and this is actually a glimpse of a particular ongoing data transmission. So it's from the middle. Why? Because C sequence number is 42, acknowledgement number is 79. That means now host A is sending a segment with sequence number 42. That means starting byte number 42, and acknowledgement 79 means previously it received, it is not shown here, but you can assume it received segment up to byte number what? 79 or 78?
78.
78. Because up to byte number 78 received by host B, then it will send acknowledgement 79. So anyway, host A sends acknowledgement 79. That means it says, okay, I have received up to byte number 78. So please send me from 79. That is for host B. But host A itself sends a new segment with a starting byte number 42, and data is, you can see, a single character. So 42, starting from 42, 1 byte, ending to actually 42, because this is a 1 byte. If it starts from 42, it's a 1 byte data. That means it's actually 42 only. So now see, host B, acknowledgements received of C echoes back. Now for the telnet, the same character receiver actually echoes. Echoes means sends back the same character. So whenever receiver sends the acknowledgement, host B sends the acknowledgement. Now see, it sends sequence number 79 because this sequence number of host B is actually acknowledgement number of host A. Is it correct? Can you understand? Because sequence number is for sender, acknowledgement number is for receiver. Now previously host A was sender, host B was receiver. So acknowledgement number was for host B and sequence number 42 was for host A. Now host B is the sender, right? And host A is the receiver. So host B will send sequence number 79. That means, okay, I am sending this character with a segment starting from 79 as expected by host A. And acknowledgement number is 43. That means what? That means host B tells host A that I have received your segment with 42 1 byte data, right? Now, next, send me from 43. Is it clear? And it is sending the same data again, data C. Now in step 3, last step, you can see host acknowledgements receipt of echoed C. Now host A again sends a new segment with sequence number 43 and acknowledgement number 80. Now in this example, every time one side is sending data with 1 byte data. That's why it is increasing by 1. But for example, let me change the example. For example, in the first segment, sequence number is 42 and data is not only a single character. Data is, for example, 10 bytes. Can you get my point? Sequence number is 42. Now assume data is 10 bytes. What will be the acknowledgement number sent by host B? You can use your paper pencil, okay? Draw the diagram. What I say, okay, let me simple telnet scenario, okay? So let me simple telnet scenario. So what actually happened here, since it's a 1 byte at a time, so it is a C means 1 byte. So every segment sends 1 byte at a time. That's why you could find that if sequence number equals to 4, if sequence number is 42, okay, by host A, then acknowledgement number is what? 43
43
by
by
host
receiver.
B, right?
Host B.
It is clear. So it's a actually it's in the example here. Okay. So it is in the example here. If you right. So if you see sequence number sent by host A is 42, and since there is 1 byte data, that's why host B sends acknowledgement number 42 plus 1. Again, sequence number 79 sent by host B and acknowledgement number sent by host A is 79 plus 1, since there is 1 byte of data. Now my question is, if, for example, if 10 bytes or 10 byte data sent by A, host A, instead of 1 byte. My question is, what will be acknowledgement number by host B? What will be the answer? Anyone?
Sir, 52.
Very good.
Yes, sir.
Very
52.
good. 52, right. 42
Yes, sir.
plus 10 equals to 52. Very good. Actually, now we can just explain a little bit. Now, if I say byte received by host B, what will be that? Is that 52 or 51?
51.
Right, 51. If you count from 42, if 42 is included, starting from 42, then starting from 42, 10 bytes will be 51. Okay, so it will be up to 51. Now the acknowledgement number will be 51 plus 1, 52. So this is the explanation. But if you just add the number of bytes with the sequence number, you will get the acknowledgement for the receiver. Clear?
Yes, sir.
Okay.
So, but sir,
that
why
is
should we count from 42? So can you please explain?
because
you
that
have
is the starting byte number. That is the starting byte number. For example, if it's okay, just let me do one more thing. I think I need to show you some hands-on here. Let me present. Okay, I think I should give you some hands-on so it will be clear. For example, when you say TCP, right? What happens in case of TCP? This is the application, right? This is, for example, socket. And what happens? Application gives data, and there is a buffer. This is the buffer. And if you think about the segments, then there are some segments here. Okay, like this. Now, suppose data is, for example, 100 bytes, for example, 100 bytes data. Now, each segment contains 10 bytes of data, right? Each segment contains 10 bytes of data, and there are some header. Just forget about the size of the header now. We are worried about how those 100 bytes of data is divided into different segments. Now, as our concept, these segment number is 1, 2, 3, up to how many segments? 10, right? 100 bytes.
Yes, sir.
So 10
sir.
segments. But these are not sequence numbers. So make it clear. These are not sequence numbers. Now, the problem is from which number I will start numbering that 100 bytes, right? I can start numbering 1 to 100. I can start numbering 0 to 99. I can start numbering 1101 to 1200. Is there any problem? There are so many options of numbering, right?
Yes, sir.
Now, we could always start from 0 or 1. But for security reason, there is a concept called session hijacking, TCP hijacking, where attacker tries to gather the information about the current sequence number. Because see, the importance here is this sequence number indicates the flow of data. So if attacker can gather the information, attacker can grab the data. So attacker tries to guess this sequence number always. So if we assume TCP always starts from 1 or starts from 0, that is very easy for the attacker. So that's why in practice, when application gives data and when there is a new connection set up, then both sides generates their sequence number with a random number. Okay, so that is the idea. Just it is part of a security course, but just to make you understand what the logic behind it, the value is created random. What that means? That means suppose this is host A, okay? Host A, and host A sends data to host B. Host B has also some data to send to host A, but if you assume only about host A, then transport layer from host A receives 100 bytes data. What that means? That means A must somehow hand over this 100 bytes data to B's process, right? That is the idea. We have already covered application layer. We are at the transport layer now. So that is the idea. Now, to transfer those 100 bytes, then TCP segments this data into smaller segments. TCP uses sequence number for this. But before converting to segments and inserting the sequence number, what host A needs? It needs the scale from which byte number, from which number it will start numbering those 100 bytes. That is where I said it can be 1 to 100, it can be 0 to 99, it can be 1100 to 12,000, 1200. It can be any value, starting value. But the bottom line is total number of bytes, how many? 100.
100, sir.
It must be 100. It cannot be 101. It can be 120. It's 100, but it doesn't matter from which number I start. It must finish by 100 bytes. And this number, random number, either 1101 or 0 or 1 or any other number, is generated during the connection establishment. We will see when connection will establish. In that case, both sender and receiver will specify this number. Now come back to the point. For example, it started with 1101. Everybody clear? This is the logic. It's a random number, so it may be 1101. Now, what will be the sequence number of first segment? Anyone?
It's 1100,
1100,
1 to 10.
1101 to 1110. Actually, 1101 will be the sequence number, and this will indicate 1101 to 1110, right? 10 bytes data starting from 1100. So that was the question asked. Who asked the question? Why we include 42?
Sir, Miss Jahid.
Yeah, Jahid. So
Yes,
now you get the answer.
Just,
So
yes, sir.
it will always, sequence number will be always the starting byte number. So in this case, it starts from 1101. So the first sequence number will be 1101. What will be the second segment sequence number, Jahid?
Sir, 1100.
What will be the 1100?
11.
Very good, 1111. See, it's clear. Very good. So it will be 1110 plus 1. And for third one, it will be 1100. 1111 to 1120. So 1121, like this. But in practice, every segment might have different number of bytes. So it might vary. Don't worry. But one thing is common. The sequence number of the second segment will be last byte sent plus 1. Now that is the acknowledgement number from the receiver, right? So you will have a connection between sequence number sent by the sender and acknowledgement number sent by the receiver. So there will be a connection. So anyway, that is the idea.
Sir, is there any particular range to generate these random numbers like 1100?
Definitely. How many bits in the header we saw? Sequence number 32 bits, right? 32
Yes,
bits. So that means you can generate from 0 to 32 to the power 32 minus 1. If
Okay, sir.
any data is larger than that, then it must be like the cyclic order. It must be again start from 0. Okay. So there are some theory related to that, but for our case, we are not worried about that. We'll try to understand how the sequence number and acknowledgement number will be used to implement the reliability. Okay. Now, let me again go back to our lecture. Okay, so let me now understand some of the scenarios as we saw in case of stop and wait. Now stop and wait, go back and select and repeat all those cases. can be implemented in data link layer also. That's why we have numbered those examples, packet 1, packet 2, right? We did not consider the byte number, that is sequence number, acknowledgement number. Now there is a basic difference in transport layer, as we already specified. It will be used by the header information, that is sequence number, acknowledgement number. So that is the basic difference. But all those examples we have used only segment number, packet number, frame number, right? So that's why packet 1, packet 2 like this. But the idea is similar. In this case also, we will implement some of the similar cases. First one, lost acknowledgement scenario. So if you think about, see, now there is no segment 1, packet 1 concept. There is always sequence number, acknowledgement number concept. So for example, if host A sends a sequence number 92 and 8 bytes of data, that means starting from 92, 8 bytes of data, acknowledgement will be 100, right? Very simple, 92 plus 8 equals 100. But lost acknowledgement scenario is definitely a timeout is set, but if the acknowledgement is lost, then what will happen? After timeout, sender will retransmit. Okay, so simple concept again, but in terms of sequence and acknowledgement. Now, what can happen? Timeout can be smaller. Maybe acknowledgement is not lost. Okay, in this case also, we can lost acknowledgement scenario, we can make this lost data scenario. Lost data scenario means instead of acknowledgement, the data itself is lost. Is there any difference in case of sender?
No, sir.
No difference, right? Because for sender, if data is lost or acknowledgement is lost, all the same. Within the timeout, no acknowledgement is received, so it will retransmit. But from the receiver's point of view, if data is received, acknowledgement is lost, then receiver has received the data. If data itself is lost, receiver has not received the data. So from the receiver's point of view, there is a difference. In this example, lost acknowledgement scenario, the data 92 8 bytes of data second time, that is redundant for the receiver, although this is not a problem. In case of receiver, if it receives redundant data, it will not store because it is already stored the data, no problem. But if the data is lost, then definitely receiver needs this data. So lost acknowledgement scenario, lost data scenario, similar. But suppose the data is received, acknowledgement also sent, but after the timeout, then what will happen? Now, in this example, you can see two segments sent back by back. It is called back by back. What this means, how many segments can be sent without waiting for acknowledgement? Because in the first example, we saw only one segment at a time. But here we could see two. It could be 3, 4, 5. How this is defined? Anybody?
The capacity of the link.
Capacity of the link. No.
Yes, sir.
No, that is not correct. Capacity of the link is not correct. Any other answer? Abu Kibriya, can you tell me what is defined by how many segments we can send? Ishtiyaq?
No, sir.
Okay, just we have discussed in the previous slide that header field window. Can you remember window size? Window size means what? For flow control. That means how much free space in the receiver's buffer. So if that free space is 200, sender can send 200 bytes. If that is 2000, sender can send 2000 bytes. We don't know how many segments we can send before it stop, because 200 may be 2 segments, 3 segments, 4 segments. So it depends on the window. previously sent by the receiver during the acknowledgement. Anyway, in this case, two segments sent. One is 92 8 bytes of data, then 120 bytes of data. Now data is received, but the acknowledgement received after the timeout, nothing to do by the sender. Sender will retransmit. Is it clear? But now how my question is, why the second one is not retransmitted? Only the first one. Why? Any logic? Okay, let me clear this. Let me make this clear. In TCP, there is a significant difference compared to the previous approaches like go back and select to repeat, where every packet has a corresponding timeout. Whenever a packet is transmitted, a timeout is set. Doesn't matter how many packets transmitted. So if 5 packets transmitted, there are 5 timeouts, each one for each packet, and it's not a fixed timeout. So maybe packet 3 timeout larger than packet 4 timeout, maybe. Okay, but in case of TCP, make it clear, in case of TCP, there is a single timer always. There is a single timer. So that is, in one sense, that is also advantageous using single timer. How you will know it, how this is advantageous when we do some examples hands-on. But for now, see, the timeout is set whenever segment 1 is sent, segment 2 is sent. But see, for the segment 2, there is no timeout. In this way, TCP timeout is used for the oldest segment acknowledgement. For example, after the timeout, sender sees that it did not receive any acknowledgement. So it will assume to retransmit, it will assume that acknowledgement for the oldest segment. What is the oldest segment here? First one, right? Because there are 2 segments.
92.
The first one is the oldest, so it will retransmit the oldest one, not the all others. Why that is advantage? See, you can see, like, actually both acknowledgements are received correctly, but since it is after the timeout, that's why it retransmitted packet 1. But from the receiver's point of view, was it necessary?
No, sir.
No, receiver has received both, but there is no way sender will understand that this is received. So that was the problem. But you can see the retransmitted segment is actually redundant, right? So we have sent 1 packet redundant, that is unnecessary, nothing to do, because this is the protocol. But if we send second packet also, is it advantageous or disadvantageous in terms of utilization?
Disadvantage, sir.
Disadvantageous. So that's why using 1 timer, TCP will never retransmit more than 1 packet. And in that case, like in this case, after receiving the acknowledgement 120, right, host A is actually confirmed, second segment is also received by the receiver. Is it clear? When sender receives the second acknowledgement, at that point, sender can be sure that receiver has received both, right? Because
Yes, sir.
if receiver did not receive both, then receiver should never send acknowledgement 120. So that is one point using single timer. So if the timer expires, always remember that sender will only send the oldest segment not acknowledged. Since both segments are not acknowledged, it retransmits the first one. Let me make this second scenario a little bit different. For example, now assume that, okay, assume that the first acknowledgement is received before the timeout, but the second acknowledgement comes after the timeout. Then what will host A do after the timeout? Did you get my point?
Yes, sir.
For example, acknowledgement 1 received before timeout and acknowledgement 2 received after timeout. What host A will do when timeout occurs? Retransmit or not? Yes or no?
No, sir.
Any other answer?
Transmit.
Because packet 2 acknowledgement is not received, so it will retransmit packet 2, right? Think. So if packet 1 acknowledgement is received within the timeout but packet 2 acknowledgement not received, then after the time, because both this timer will work for both the segments. In that case, packet 1 acknowledgement is received but the packet 2 not received, so after the timeout it will retransmit the packet 2. One more thing here,
Sir,
see,
sir, one timeout will work for all the segment.
right, for all the segment. So after the timeout, sender will see which segment it did not receive the acknowledgement, which oldest segment it did not receive the acknowledgement. Now in this case 1 2, if 1 is received then 2 is the oldest. If there are 5 segments, suppose 1 received, 3 received, 4 received but 2 did not receive, then 2 is the oldest.
Yes, sir.
Okay, we will go through many more examples, then it will be more clear, but just keep in mind one timeout is at a time used by the TCP. Doesn't matter how many segments it sent, but only after the timeout it will check whether all the acknowledgements are received. If it did not receive for particular packets, if it did not receive for 3 segments, then which one is the oldest? It will only retransmit the oldest and then again set the timeout, and then after the timeout again it will decide this will go this way. And another point here is, see, cumulative acknowledgement. So after the retransmission of sequence number 92 8 bytes of data, see, it did not send 100, it did not send 100, it sent 120. Why? Because receiver will always return the updated acknowledgement until that point from where there is no gap. If there is a gap in the middle, then it will send the acknowledgement before the gap, like go back and, but there is no gap. So even if it received 92 8 bytes of data second time, receiver understands this is a duplicate, but receiver will not send 100, receiver will send 120. That is one example. And the last one, I think we are at the end of the class, but this is another very interesting example. I will end with this. Here you can see again both the segment is received, and you can assume the first acknowledgement is lost, but the second acknowledgement is received within the timeout, not after the timeout. What will happen after the timeout? Assume that the acknowledgement 120 is received before the timer expires. Then what sender will do, host A will do? Will it retransmit anything? Yes or no? Very important question.
No, sir.
No.
No, sir.
Why? Why, Bidhan?
No, sir.
Bidhan, can you tell me why? Logic?
Sir,
Because it has
Sir,
received
second
both, right?
second acknowledgement পেয়ে গেছে স্যার।
Right.
So, sir,
Sender, correct. If sender receives 120, that means sender can assume receiver must have received both. Otherwise, receiver will never send me 120. So, although sender did not receive 100, it received 120, it can assume. Now, why? Because of that cumulative acknowledgement. At the start of next class, I will show you some example why this happens, why this cumulative acknowledgement is advantageous. But in this example, we already saw what is the advantage. Although it did not receive an acknowledgement, it can assume, it can not assume, it can be sure that receiver has received both. Okay, so that's why see it will send a new. This is not retransmission. This is a new segment sent by the sender. So this is the three scenarios. I think this will make our concept clear. So please go through these scenarios from the textbook. In the next class, we will do some hands-on again based on TCP, where you have to understand the TCP header. You have to understand these three scenarios, and then we'll do some exercises before going to our next topic. Any question? Okay. Okay, let me take the attendance. Let me take your attendance first. Oh, we have 1 minute only. So please respond first, okay? Abu Abdullah, Kamrul Islam Tushar. Okay, those who has mic problem, please put your ID and name in the message box. Kamrul Islam Tushar, Imtiaz Hussain Shobhon.
Sir, Kamrul Islam
Present, sir.
Okay, Kamrul Islam Tushar present. Imtiaz present. Abdullah Al Rifat.
Yes, sir.
Okay. Inamul Haq.
Present, sir.
Imam Reza.
Present, sir.
Rifaz Nahian.
Yes, sir.
Rifaz.
Sir, Asif.
Okay. Rokunuzzaman Khan. Rokunuzzaman. Bidhan present. Laila Ishrat.
Asif, sir.
Yes, sir.
Okay. Farah Farjana. Okay. Farah, I think is sick. Okay. Fazle Rabbi.
Yes, sir.
Okay. Priyabrata Nath.
Yes, sir.
Ifat Rafsan. Ali Ahmed.
Yes, sir.
Okay. Kaushik present. Khurshida Jahan.
Sir.
Present, sir.
Okay. Shakhawat Hussain. Shakhawat Hussain. Samir Ahmed.
Yes, sir.
Mahmudul Hassan. Mahmudul Hassan. Okay. Fahim Shakil. Abu Sajjad.
Present, sir.
Okay. Nibirud Jaman. Sadman Shakib.
Yes, sir.
Adnan Kobir.
Yes, sir.
Okay. Dihan Pathan. Dihan, you are present, right?
Box sir.
Okay. Miraz Farooq.
Yes, sir.
Okay. Taki
Present, sir.
present. Shahadat present. Rakibul Islam. Al Shahriar.
Yes, sir.
Yes, sir.
Okay. Tanvir Hassan. Yes. Tanvir present. Tanvir Hassan.
Sir, sir.
Okay. Sakib Hussain.
Yes, sir.
Okay. Mashuke Alam.
Mashuki Alam.
Okay. Shah Alam. Sabbish Sarkar.
Shalom,
Okay. Shah Alam present. Sabbish Sarkar.
Yes, sir.
Okay. Abdar Sadiq.
Yes, sir.
Ishtiaq Ahmed.
Yes, sir. Present, sir. Ishtiaq Ahmed.
Okay. Jahidul present. Mofile.
Yes, sir.
Mahfuzur Rahman Sifat.
Yes, sir.
Okay. Shafiqul Islam. Shafiqul Islam. খন্দকার শ্রাবণ, আমান্তা হোসেন,
Present, sir.
আবির রেজা,
Present, sir.
ওকে, খালিদ রিদওয়ান, শাহরিয়াজ,
Present, sir.
ওকে, তাহমিনা তানজিন, তাহমিনা, মোহাম্মদ মাহফুজুর রহমান,
Yes, sir.
ওকে, ফজিলা প্রেজেন্ট, আশরাফুন নাহার প্রেজেন্ট, শিফা চৌধুরী,
Yes, sir.
ওকে, মেজবাহুল আলম, মেজবাহুল আলম, ইয়াসির আরাফাত,
Present, sir.
ওকে, সুদীপ প্রেজেন্ট, আবু কিবরিয়া প্রেজেন্ট, আব্দুর রহিম প্রেজেন্ট। Okay, anyone? Okay, just put your ID and name in the message box. I will update later. Okay, thank you very much. Then see you in the next class.
আসসালামু আলাইকুম স্যার।
Allah Hafiz. Wa alaikum assalam.
Assalamu alaikum.